Good, good. All right, hello everybody, and thank you for sticking around. I know it's been a really long conference, but you've just had your brains crammed full of awesome stats and probabilistic goodness, and we are hoping to continue that now. And my name is Mitzi Morris. I'm a member of the STAN development team. I work up at Columbia with Andrew Gelman. And I am going to talk about Bayesian inference for you, with you, to you. So let's get some general remarks and review. And what we're going to talk about is multi-level regression models in STAN, and then ways to evaluate inference. So STAN, how many of you are using STAN? Okay, good. How many of you would like to use STAN? How many of you have heard of STAN? Great, okay, this is better. Great. So STAN is named after Stanisław Ulam, who originated Monte Carlo estimation. So we'll start with the story, and the story is how Stanisław Ulam came up with the Monte Carlo estimation technique, which is that he was working at Los Alamos on the Manhattan Project, and he got sick, so they sent him to the hospital. And in those days, if you're in the hospital and you're working on a super highly classified top secret project, you do not get to VPN back to the lab. So he had nothing to do in his hotel room but play solitaire. And as a statistician, he looked at solitaire, the game, and said, well, what are my chances if I have a perfectly shuffled deck of cards and I deal myself out the solitaire game, what are my chances of winning? And so from probability theory, you should be able to start having 52, choose 1, 51, choose 2, blah, 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 for all of your stuff. And he realized that he just couldn't figure out what that big combinatorics was. And this was distressing because he thought he should be able to do it. And in the end, he just played games of solitaire over and over and over again and counted up the number that he won and the number that he lost. And at the end, he had an estimate of his chances of winning any random game of solitaire from a well-shuffled deck. And so that is essentially estimation by simulation. You simulate a whole bunch of times, and that set of simulations are your sample. And at the end, you look at your sample and you compute over the sample and answer the questions that you want to answer using the proportional information that's present in your sample. Okay, so that's it. That's Monte Carlo methods. And they're called Monte Carlo methods because there's a famous casino in Monte Carlo where you go gambling, and so everything there is random. So it's all about randomness. STAN is a probabilistic programming language. So it's a domain-specific programming language. And what you are doing in the STAN language when you write a STAN program is you are expressing the total joint probability of all the parameters in your model. So we're going to get to that, and we'll see lots of examples. STAN uses the STAN NUTS HMC sampler, which does Monte Carlo, Markov chain Monte Carlo sampling. And this is what sort of took STAN, and there were already probabilistic programming languages using Bayesian techniques, bugs and jags. STAN is an order of magnitude more powerful than they are, precisely because the Hamiltonian Monte Carlo, that's the HMC in HMC, Hamiltonian Monte Carlo is a very efficient way of doing this simulation, these random jumps around posterior probability density, and it works really well when you're in super high dimensions. And by super high dimensions, I mean, more than 3 or 4. more than 10, definitely more than 10, but think about what you're doing in any given day when you're trying to answer some kind of questions about your data. You're usually trying to get all these features. And if you're doing something like natural language, the amount of features you have are very, very, very big. Even if you're just collecting information about your population, about your users, you've probably got a dozen features, 100 features. That's a very high dimensional space. Each feature is adding a dimension. And these make things very challenging. Usually there's a lot of correlations between different features in your data, and this is going to be difficult to compute. So the Stan Hamiltonian Monte Carlo method does a very efficient job of giving you a representative sample from your complicated posterior space, complicated geometry space of the probability of all of your parameters. Stan has been around for about 6 or 7 years now, and almost all of the people who were originally using Stan were people who were working in R. So the R ecosystem for Stan is very, very rich. And I started working on a Python interface to Stan in January of this year, which we're calling Command Stan Py. And because I think that, people in the Python community should be using Stan and should be doing Bayesian data analysis. And actually, I don't care if you use Stan, but I do want you to use Bayesian data analysis. And Stan is open source, and Command Stan Py is BSD licensed. And what we're talking about today is multi-level modeling. It's a kind of regression modeling. It's what you want to do. And as Cam was talking about, there's this notion of pooling. We're going to see exactly how pooling works and what we mean by pooling information. And there are a lot of names for these. So, and there's also a blog, Statistical Modeling, Causal Inference in Social Science. And Bob Carpenter put up a post one day about all the names for hierarchical and multi-level modeling. And it's a really nice post because he gives you insight on all these names, just exactly what that group of people meant when they decided to build their multi-level model and why they named it the way they did and how it differs from everybody else. So what you find in the domain of science is that every group was trying to solve a problem. They consulted their statistician. They came up with really, really, really great techniques that are pretty much the same thing as what they came up with the lab down the hall. And they all published, and they all published independently. So pretty much every model that you want to use for your data has been developed by somebody else for their data. And it's just the challenge of finding them and communicating is really difficult. And that's what makes working on Stan so much fun, because our user base spans the gamut of every single kind of user. Anybody who's got data is talking to each other on the forums, and we're all learning from each other. So, statistical inference. We learn about unknown or unobserved quantities of a process from the data generated by that process. So what we're doing, in contrast to machine learning, especially those of you who are like, gotta do some deep belief nets, gotta do some deep learning. That's a really, really, really great, and there are many, many, many cases where that's really the best thing you can do, and you should go ahead and do it. But there are also cases where you're not going to be able to make that fly, in which case you would be well served by looking into STAN. And what we're doing when we're doing Bayesian modeling is we're trying to do a kind of a white box model. We care about your data generating process. And what we're going to do with your generated data is we're going to try to build a model and work backwards from the data to find out more about your model, especially when the parameters in your model are actionable items. So that's really for a policymaker or for a business decision maker or for a scientist. You care about what those parameters are because those are the things you can change. And so by having a model where all the parameters are clearly labeled, they're giving you a bunch of levers, a bunch of dials on your process, and you can tune them and tweak them and then ask yourself what's going to happen. And that's generally what people want to do. So that's why Bayesian methods and Bayesian models are really, really the way to go. And the Bayesian workflow is one where you spend some time thinking about the model, thinking about the data generating process, and you don't need to worry that much about your distributions or your math. You're asking yourself, what are the dependencies? How are things related to each other? And especially for multi-level models, you want to know what things are nested inside of each other. Is there interesting structure in the data that's coming in that should be reflected in the model that you're developing? Once you've got your model, then you're going to use a tool like STAN to do the estimation. That's just taking something down off the shelf and running your data through it to get an answer. What you care about is afterwards, you don't just take that answer and run. You sit back and you look at that answer and you interrogate that answer and you say, hey, wait, is this really what I expect given what I know about the world? Because the other thing that Bayesians, this historical Bayesian frequentist debate is all about not putting your thumb on the scale, right? Bayesians are putting their thumb on the scale. Well, okay, so what? It's not like everybody. Let me try to make that sound less defensive. We're using what we know about the world, and no matter how you build your model, you're cooking in what you know, you're cooking your expectations into your model. So we're being honest, and we're thinking very hard about what we know, and we're going to ask ourselves, is this what I expect, given what I know, at every step of the way? And that's really all that's going on. And what we want to do with this Bayesian workflow and what the people who've worked on STAN, the set of tools, especially this downstream ecosystem of visualization and model checking are trying to do is we're encouraging you to develop as many variants of a model as you need to give yourself the answers of what's the minimum I can get away with, what's the maximum I should be doing, playing around with what you know about the problem you're trying to solve. So we're really trying to facilitate engagement with the question that you're trying to answer more than anything else. Statistical notation, just so we can be clear, and you've seen this a bunch today, right? Nothing scary on this slide? Great. Then we'll just go on. Bayes' theorem. Have we seen Bayes' theorem today? Everybody happy with Bayes' theorem? Okay, so let's go over this slide. What we're interested in is we've got the conditional probability. And for Bayesians, the important thing that we're working with is the posterior probability distribution. We've collected our data, we've built our model, we've run our data through our inference engine. What we have at the end is we have a posterior probability distribution, And that's what we want to work with. So in this slide, what's most important is to notice that in this probability of theta given y, it's the probability of your parameters given your data. And I started doing statistics about a dozen years ago. And I kept driving my husband crazy because I would just, write down probability of y given theta and probability of theta given y. And my husband's Bob Carpenter because he developed Stan originally. And he'd be like, what? It's confusing, okay? It really matters. It took me a while to master this, so it's okay if it takes you guys a while to master this too. But we care about the posterior probability distribution. Hello, my little thingy here. And when we build a Stan model, what the Stan is computing is it's computing the total joint probability density of all of your parameters and your data all at once. And it's really cool that it's doing this. And when you are writing your model, you are supplying the priors on your parameters, and you are coming up with your likelihood function. This is what you supply to your Stan model when you develop a Stan model or any Bayesian model. And this is what you get. And it's really nice that you've got this proportional constant because that makes things go a lot faster. Any questions on this one? No? And the reason that we want to be Bayesian is that we want to be able to actually think about our posterior distribution, the probability of theta given y. We want to think about it as a full probability distribution so we can get the mean, median, mode, and crucially the standard deviation, which is what gives us our uncertainty. And there was a woman here who asked a question about credible intervals. If you're doing Bayesian data analysis, the credible intervals are whatever boundaries you want to put on your posterior probability distribution. So you can have the 95% central confidence interval, which is 2 standard deviations from the mean. And when you have a full credible interval, you can look at the quantiles in that credible interval. You can figure out whether or not you've got a really sharply peaked posterior probability distribution, meaning, yeah, almost all the time I know that all my data is going to be here and it's going to look just like that. Or you can have a very, very broad, shallow sort of a posterior probability distribution, which means, I'm not so sure about what I know. I know that it could be, between 2 and 98, but gosh, I really don't know much more than that. And that's really useful information for you to proceed in any kind of a decision-making situation. So Monte Carlo simulation. What do we mean by a sample? I think what we mean by a sample is that we've got somewhere in our back pocket, we've got a random number generator. And we're going to be able to generate quantities, random quantities at will. And a classic example of Monte Carlo simulation is calculating pi. It works really nicely because you can take your random number generator and you can generate numbers between -1 and 1 really easily. And if you do that for xy points, you've now got a rectangle which has an area of 4, and you have a unit circle, and the area of your unit circle is pi r squared. And then with just a little bit of algebra, you can count all of the points with a simple mathematical formula. Is x squared plus y squared less than 1? Great, they're in the circle, otherwise they're out of the circle. What's the proportion of points in the circle? pi is your answer, multiplying it by 4. And so you can do that in Python, and I did that in Python. And I did that in Python 100 times, and my estimate of pi was 3.5, which is kind of a ballpark estimate. And then I did it a little bit longer, and I started to get pretty close, as much as I needed to know about pi, and it took more and more time. And the point of this slide is that when you're using these estimation by simulation techniques, you need a sample, and you only need as big a sample as you need to get the precision, the accuracy that matters to you. So if you don't have a need for 5 decimal places of accuracy, you don't have to go there, because it'll take a long time. The Hamiltonian Monte Carlo, I said a little bit about Hamiltonian Monte Carlo. I can't say anything more about Hamiltonian Monte Carlo and get there in this. But if you're interested, I love this paper. It's a really nice, and there's a link at the end of my slides. I put a link to this paper. It's a really nice example of how Hamiltonian Monte Carlo works. And it compares it to Gibbs samplers, which some of you might have heard of, and shows why you really want to be using Hamiltonian Monte Carlo. And there are, as I mentioned, PyMC3, Edward, and Pyro are all using Hamiltonian Monte Carlo. So I'm not here to tell you you have to use Stan. I'm just here to tell you you should. Let's go on to linear regression. Linear regression is, everybody know linear regression? Good. So here's your canonical example. You've got just a simple pair of x, y predictors. X is your data, y is your observed outcome. You want to create a model of the data generating process for y, and you're just going to put weights on your x's. So you're going to figure out where's your intercept and what is the slope of the line, and now you can draw a line through your cloud of points that minimizes the distance from every y to its y on the line. So it's a vertical distance, and it works out really nicely in terms of the squared error. And when you have a regression model, you are saying that my regression model is going to fit my data with some amount of random error. And that epsilon is considered to be random noise, independent random noise. So epsilon has the distribution of normal centered 0 with some unknown variance sigma. That means that we plug x in as the estimate of our mean, and we use sigma as our variance, and there we have it, a Stan program statement which says that our observed data y is drawn from a normal distribution with mean alpha plus beta times x and variance sigma. So this is your first example of Stan syntax. And Stan syntax was developed to look like bug syntax or R syntax, and I think there are things in Python where you might be using this sampling notation. So our first example is Major League player batting ability. There's a very detailed case study. I generated the PDF from the case study, and it ran to 60 pages. It's a great case study, and my goal today is to get you through the highlights of this so that you can then dive in and appreciate the goodness in this case study. And we're looking at baseball players. I mean, statistics in baseball are just like, beans and cornbread. What we've got here are data for Major League Baseball players. This is based on a case study that was done by somebody named Brad Efron, Bootstrap Brad, if you've used the Bootstrap technique. Efron and Morris, and he's not related to me, but, you know, it's too bad. And what they did was they looked at the 1975 Major League Baseball season, cherry-picked a couple of interesting cases of, you know, good players and not so good players, and they looked at their first 45 at-bats, and then they had the stats on the rest of the season. And there are three ways that we can look at deciding what the predictions we should make about the number of hits that a player gets in a certain number of at-bats. We can say that all players are exactly alike, and so all we need to do is estimate average player ability. We can say that all players are snowflakes. They're very special, and each player gets his own model, which you guys might be doing in some of your applications, right? Every stock has its own model or something. Or you can try to do the multi-level thing, which is what everybody really, really wants to do, which is to say that, okay, we have a general population of baseball players. If you're a Major League Baseball player, you probably fit this profile. And we know something in general about what all Major League Baseball players look like. And we know that players differ from player to player. So we have what are the group level effects and the individual or random effects. And so that's what our multi-level model is going to do for you. And then we're going to show you what the results of setting up these three models look like. So to model player batting ability, we're using a binomial distribution. That is to say, we have a number of at-bats, and during that number of at-bats, our player got a certain number of hits. So that is the distribution on the bottom. Hello, laser pointer. So we're going to calculate the probability of, say, getting 18 hits in your first 45 at-bats, given that you have an ability theta. And this theta comes from your Bernoulli, from your coin flip model. You've got a binary outcome. You get up to bat, either you get a hit or you don't get a hit. Here are our players. These are the top players and the bottom players in this 18-player example data set. Roberto Clemente, in his first 45 at-bats, in the 1975 Major League Baseball season, got 18 hits, which would give him a batting average of 400. Are there any baseball fans here? Okay, so what Major League Baseball player ever had a 400 average? Ted Williams! Yes! You get a stand sticker for that one. Yeah, so we don't really, I mean, Roberto Clemente, don't get me wrong, he's great, but do we really think that he had a 400 batting average? I don't know about it. And this leads to the next question is, why did they use 45 at-bats? Well, he probably didn't get a hit on at-bat number 46 or at-bat number 47, because then they would have gone up to 50, you know? So when you get your data, you should interrogate your data from the get-go. In any case, this is the example we're working with. And if we plot, so this plot is showing you the individual batting averages and the average batting averages. So these are your two choices for models number 1 and models number 2. And this is a little bit more a quick review of the binomial distribution. What's cool about the binomial distribution is it is giving you a integer value output. So this is, for this distribution, we don't have any information. There is no getting a hit 14.5, right? Either you're going to get 14 hits or you're going to get 15 hits. And if you had a 400 batting average, you, in 45 at-bats, might only get 11 or 12. That is within the credible interval. And you might get 24. And when you think about this, you begin to understand when you're watching the World Series and every time a player got a really good hit, he's going, yeah, yeah, yeah. I got lucky. Really, it's pretty random. So, yeah. And what we're going to do is we're going to show you some Stan models, and I'm going to try to go as quickly as I can through Stan because I don't want to get bogged down in teaching you how to write Stan programs because it's learning another programming language. But I will say that Stan, as a programming language, has a syntax which is not Pythonic. Sorry. Your variables are strongly typed. Your blocks are enclosed by curly braces. You have ordered blocks, and the named blocks are calling out the important parts of your Stan program. This is a really, really cool feature of Stan, but it's a good thing and a bad thing. It does make you think about what is my data and what are my parameters. At the same time, when you're writing your Stan model, it doesn't always make it that easy to see the data generating process story told that cleanly. And so there's a lot of talk in the Stan community about how we're going to change the Stan language and possibly make Stan programs different to write. So another reason for not going into Stan right now. That's pretty much all you need to know about Stan. Syntax. And again, in a Stan program, you declare all of your parameters in a special named parameters block. And then in the model block is where the Stan program computes the joint log probability density of the parameters and the data. So the model block special, parameters block special, data block also special. Here is a multi-level model in Stan. It's taken directly from the case study. So we have a parameter phi, which is the population chance of success. So that looks like our Bernoulli phi. If you compare it to here, in the all players are all alike, we call that phi. That's your average player ability. And for all different players, we have a vector of parameters theta. So here in the multi-level model, we have this phi and we have this theta, and we have a kappa, which is prior on our prior. And the case study goes into why this particular parameterization was chosen, and it's very interesting to follow because there are some difficulties with this parameterization. This is not that easy to fit. And you could make your model more efficient by reparameterizing, which is, again, a very important part of building a model that you're going to drop into a production workflow. It's got to compute in real time. So in this model here, we put a hyper prior on our prior. And then we compute our prior and our likelihood. No, this is our likelihood. This is our prior. This is a hyper prior. Okay, what I said. And so when we fit this model, we see that the orange is the outcome of using the multi-level model. And what it does is it smooths out our estimates. It lets us say that the best players are better than the worst players or not so hot players. But they're more alike than we thought they were. So in this visualization, the very last bar here on the right is the complete pooling model. So it's not really a player, but I put it in that way instead of drawing the average line across. Okay. Would you like to see how this works? Or should I go on to the next soccer model? Let's see how it works. So I've put the links to these notebooks and all of this data up on the Stan website, and I posted in the general Slack channel so you can download these slides and this data set. This is the data set, and here's the link to the case study for you. So we're going to use command stand Py, which is a lightweight wrapper around command stand, which is the command line interface to the Stan inference engine. So we'll just make sure that we're using Stan, and oh look, we're using the very latest command stand 221. Here are our baseball players, and yep, that's the data. And then we're going to plot oh yeah, there we go. And this is just the plot that I created to show you. So this is using, oh no, wait, this is just plotting the data. Right. So what we have to do for command stand Py is we're going to munge out the data that we want to feed into our model. We're just munging the data here. So we're going to feed in a data dictionary. And what's going to be in that data dictionary are the names of all the variables that are in the data block of the model. And just for fun, this is how I computed the binomial distribution, which was in that the plot we looked at. That's not really very interesting for what we're doing now. So now we're actually going to go through command stan, and we are going to we're going to declare our model, and once we've declared the model, it's a file on disk. We can examine what that is, so we'll print out the code for the model. Then we're going to compile the model, and then we're going to do the fit, and then we're going to get the summary of how well the model fits the data. Okay, so bombs away. And you can see that it is right now compiling the model while we admire the model. And it's going to take about 30 seconds. Whew. It took much longer to compile that model than it did to run 4 chains. So sampler chains. Are we familiar with sampler chains? Okay. We're doing Markov chain Monte Carlo. So what command stand Py is doing is it's firing off 4 parallel processes where the Stan model is starting and it's taking the data and it's doing this Markov chain Monte Carlo, so that's a chain, and it's giving you a sample. So the reason we want to run multiple chains in parallel is not that we care about whether or not they're parallel, but when we're done, we want to compare all the chains against each other because we've got this Hamiltonian that's jumping around in this complicated posterior space. And if you have coded your model and made a mistake somewhere along the way, or if you just have the wrong model, or if you've just really done something super stupid, your sampler will get stuck. So what you want to see, if you've got a good, if you've got a model that is well-conditioned, appropriate for your data, you want to be able to know that whenever you fired up a chain, that you got this nice, super random behavior. And so you're going to compare a bunch of chains against each other, and you're going to look for the absence of any patterns whatsoever, within chains or across chains. And if you get that behavior, then you feel like, okay, I've got the proper conditions for me to reason about this sample. This sample truly is a random sample. It's generated from a process. It's ergodic. It's reversible. It is all these good things. I actually can trust that I've now got a proper sample from my posterior distribution, because if you don't have, if your model hasn't converged and you got a sample, you've got a sample from crap. It doesn't mean anything. You cannot use this data. So we like this data because this actually is correct, and then we've got all these draws. We've actually got 4,000 draws in our sample from the posterior. Now we can compute statistics over them, and we see what's most important here is that we have phi is 270, 0.27. So we're saying that your average baseball player has a 270 average. Fine, works with, that's pretty good. And now we're going to do exactly the same thing, just to show you that we can do it twice. And this is the second model. Again, it's taking a little bit of time to compile. And in this model, we're just going to, yep, there it goes. And now what we've got is we've got estimates for every player. So player number 1 is Roberto Clemente. In the data, we saw that he had a 400 batting average. We've been doing taking a random sample. And in our random sample, we said, well, really, the 50% quantile is at 400. And for some reason, it's telling me the mean is at 0.41, but that's because I rounded to 2 places. So they're probably much closer. Critically, what you really want to know is, did my model converge? This is the R-hat statistic, which is making sure that all your chains have mixed and are perfectly random. Yep, my model converged. R-hat has to be 1 or 1.0. If it's 1.1, no good. And what we see is we have the number of effective samples in our sample. Oh, no, this is the number of effective samples per second. This is how fast, how efficient our computation is. This is the number of effective samples, which is pretty cool because we ran 4,000 draws, but there was anti-correlation. So our sample actually is giving us information, more information than we thought we could squeeze out of 4,000 draws. We're actually getting the equivalent of 10,000 draws from the posterior, which is really cool. And then finally we get the model here, the simple hierarchical model, which is a little bit more complicated in terms of the amount of code. Like it's got like 6 more lines of code, and it takes the same amount of time to compile, and it fits beautifully. And now we've got estimates for our group level predictor. 270 is our average Major League Baseball player's batting ability. We've got this kappa score, that's the hyperprior, and we've got theta for Roberto Clemente, and we think Roberto Clemente has actually got about a 320 batting average, given what we've seen and what we know, which is still like really super good. And so, as I said, this model was difficult to fit. What you might notice here is that I added this parameter adapt delta to my sampling statement. That meant go a little slower, take a little bit more time, because we know this model is not going to do the right thing. And here, if I say diagnose, I get these diagnostics. And wow, yeah, see, still, not good. We got some divergences, so maybe I should actually up the adapt delta. You should actually read the case study to go deeper into the problems with this model. And finally, we do some visualization, and voila, that's it. Okay. Questions, yeah. And while we're doing questions, it's been a really long day, so I brought chocolate for all of you in case you're... What would you like to know?
Do you have a notion of regularization?
Well, that's what hierarchical models are. Can you pass this around and open it? I mean, overfitting. Well, the regularization is the same thing as putting a group level effect on your data, and you can overfit this model I don't think is overfitting the data because it's a pretty, I mean, overfitting the data would mean that we would like crank up the priors so that we would start in the right place. You can always build a model to overfit your data, yes. This model is pretty general. But if you don't have enough data, then maybe you shouldn't, really consider these parameters to be what you want to reason with. Does that answer your question?
Well, and also how sensitive is the model to outliers?
Yeah. Well, that's the that gets back to the whole Bayesian workflow. But I mean, that gets back to the whole Bayesian workflow. When you're interrogating your fit afterwards, you do want to know how sensitive are you to outliers. So you would take your fitted model, and this is where replication comes in. So we're going to see that in the next example. So just keep that question in the back of your mind. Okay? Yes?
So I have a question.
Yes?
What is the problem you solve? I believe you solve using an analytic solution.
Yeah, sure. Yes. Well, can it? No, I don't know about that.
It's so, but anyway, like I also heard that recently that someone was benchmarking Stan against some other ways of doing regression in Python. And Stan outperformed like a lot of other things fairly significantly. Why would Stan outperform on these things?
Oh, what a great question. Because Stan has autodiff. Stan's autodiff library is built in C++. So Stan implemented its own autodiff library, and it is really seriously fast. So Cam was talking about autograd. The thing of it is that when you're setting up that automatic differentiation, how you evaluate how you evaluate those functions, how you set up the calculation of the gradient, you should do it in a super smart way. So you should figure out which steps are going to be computed over and over again and how you make sure that everything is memory local, and you do it out the wazoo. So Stan is built on a very high performance C++ automatic differentiation library. And Stan was built to be fast because Andrew Gelman is sitting there at every meeting, and all he says is, I want my models to fit faster. Okay, so we've got people who really care, and they're our boss. So, answer your question? Great. Okay. Yes, I was actually going to make you guys, are we okay? Because otherwise I'm going to make you get up and do jumping jacks because it's been a long day, but you seem to be okay. So that is baseball, and the second example is just, it's another example of setting up a model and looking at the data. And it's the Women's World Cup. So Nitya here is like, thank her for this model because she worked through it and I worked with her, and it's really, it was a total blast. We did this with the PyLadies. Why did that say that? Anyway, okay, that was in the wrong place. This is paired comparison. So now we're no longer talking about individual baseball players, we're talking about teams, and you want to know which team's going to win. And when you're trying to figure out which team's going to win, it's often the case that you've never seen these teams play each other before, or you have seen them play each other before, but you think that you can do a better job than just like counting how many times previously, Ohio State beat Michigan State or whatever. What we want to do is we want to estimate the team ability based on the match outcome, and we are going to use a linear model to model team ability, and it's going to have group and individual level characteristics. So another multi-level model, same thing, a little bit more complicated. And what we're interested in is when we've got a soccer match, we're not going to model it in terms of just who won and who lost. We're going to model it in terms of the score differential. So if Germany scores 3 goals and Nigeria scores 2 goals, then the score differential is 1 in favor of Germany, and so on and so forth. And what we're looking at here is the visualization we get to in the end of the model, which is that we're going to estimate our uncertainty by using replication, and this is called posterior predictive check. So at the end of each, well, we'll see it when we get to it. Our data. Our data are the 48 matches up through the quarterfinals of the Women's World Cup. There were 24 teams, and everybody had played some amount of the other teams, but not all of them. And we have the date, the match list, the teams, and the scores. We also need to put a prior. We don't know very much about our teams, so we're going to bring in prior information, which is just a single number called the Soccer Power Index, which is on this blog by Nate Silver, Mr. 538. He explains what the Soccer Power Index is. So according to the Soccer Power Index, the U.S. was heavily favored, U.S. women's team. And then there were going down to 37. So it was a scale out of 100 points. And what we do in our STAN program, again, just reviewing what a STAN program looks like, you set up your data, and we're going to take in, I is going to be the number of teams, and we have a per team soccer power index, and then we have N matches, and what we're doing is this is, 4 parallel arrays that are essentially a row of a database table or something like that. What you see here is that you can put bounds on your strongly typed variables, and statements are executed in order, so you have to declare I before you use it, but you can do that nicely. In the transformed data, so this is a new data block. The transformed data block is executed once when the model is instantiated. This is where you can do work that's only going to be done once, so you can do it sloppily in an expensive way where but it allows you critically to take your data in the way that it comes in from the wild and then transform it on the inside of your STAN program, so that you don't ever have to worry about munging your data in the wrong way and then somehow the model doesn't work with the next data set. So you're going to be always treating your data the same way, which is really super nice. And what we're doing here is we're standardizing our soccer power index ratings so that everything is centered on 0 and you have a variance of 1. So this is your familiar, this is sort of your putting your standard, your soccer power index on the Z-scale. So we're calling it the SPI standard. And this is just STAN as a programming language, has 4 loops and super powerful, cool indexing, and a really, really, really rich library of built-in statistical functions, and every distribution you want. Somebody has probably implemented it, and they've probably implemented a vectorized version of it too. Okay. And the parameters on our model are the per team random effects. You can see that it's per team because it's got like a vector that's the length of the number of teams. And you can see that this is group level because it's just a scalar. So these are the 2 components of our linear regression model for the team ability. And in the and we put variance terms on the per team variation. So we've got a random effect. That random effect has both the mean and the variance here, and we have overall noise in our estimate. And the transformed parameters block is done at every step of the sampler, and it takes the current estimates of the parameters and then it runs this calculation, and that's what you use at the point when you're actually fitting the model. So here, the ability is not a parameter. It's a quantity that we have to use when we're calculating the other parameters in the model. So by virtue of having this transformed parameter ability, when we compute with the ability, we will be making the proper inferences about all of the parameters in the model. And we always put priors on our parameters, and here we're putting priors that are fairly weak priors.
What's the units of the priors?
Sorry.
So what sort of assumptions are your priors making?
These are pretty minimal, and somewhere, at the end, I do, did I put it in one of the previous slides? There's a link in here to our prior choice recommendations, but that's an excellent question. These are the current thinking, that basically these are weakly informative priors saying that we expect things to be centered at 0 with a certain amount of variance.
So how would you know if you chose something unreasonable? Like if alpha wasn't, if it was a bad idea to center alpha at 0, like
The model would have
how
a,
would Stan tell me that I would
well,
indicate I should adjust?
the model might have a really hard time fitting. The diagnostics might not be good, but this is where your model checking would come in. But also, your priors reflect what you know about the world, so you should be, it's a question you have to answer, but the Stan forums are a good place to get advice, and as I say, we've got the wiki page, because there's like tons of questions around exactly that issue. So in the generated quantities block, which we haven't seen yet, but we're going to replicate our data. So now we're going to produce a sample where at for every estimate of a parameter, so for every draw from the posterior, we're going to use that draw from the posterior, and we're going to run it through the data generating process, again using the random number generator, to push our uncertainty through to see what we would get for data if this was the true parameter. Everybody follow, or did I? Yeah, great. So that's what we're doing here. We're using replication, and this is going to give us a handle on our uncertainty that we can use to draw those credible interval lines in our visualization. We could also, in our generated quantities block, set things up to do prediction, which is really what we want to be doing. If we were doing prediction using this model and this regime, what we would need to be doing is we would need to be feeding the data that we want to make predictions about into the model along with the data that we're using to actually estimate the parameters. So we would actually have to, in our data block, add the indices of the teams that are going to be in the semifinals. So there's going to be 2 semifinals, so we've got 2 teams, and we have to get all the indexes lined up properly. But then in the generated quantities block, we're going to look at, for the 2 semifinals, we're going to look at each semifinal game match, and we're just going to say, oh, okay, I know the abilities for these teams now, let's just draw from a normal. And shouldn't that be normal RNG? Yeah, that should be normal RNG, yeah. So, yeah. Oh, no, actually, maybe it is. Maybe that would work. Anyway, let's do the IPython notebook. And so, yeah, so this is the second notebook. Oh. Yeah, this notebook, right. Okay, so yeah, everything I've said is true. We don't have a lot of data, and we have different players on each team, and we do have some player data. So the soccer power index is going to be a really huge crutch here in terms of really big prior, not a lot of data. And this is the World Cup data that we've already seen in the slides. And we'll just get it all loaded up. And this is the soccer power index, where you see that these are the top and the bottom countries in terms of their things, and the stand code. And the model is taking some amount of time to compile. So this is the full program, everything lined up. And we've seen all of these things in the slides. In this program, we're not actually doing any predictions. So our inputs are just on the, we're just looking at the quarterfinal information, and we haven't asked ourselves who's going to be in the semifinals or the finals. So this is just the model that does replication. So, yeah. So let us fit that. And this time I actually assembled the dictionary that you want as an on-disk file. And we will just run that model and let it fit, and whoa, there we go. And all of the things in the model, so we have 24, so all of the variables in the model now in the parameters, transform parameters, and generated quantities block, we have a vector alpha, we have alpha, beta, sigma alpha, and sigma y. So we're going to get all of those guys in our sample. We're also getting the ability, which is what we really care about. And we are also getting a vector of length 48 for the 48 matches, which is the estimate using all of the team estimated abilities. We're getting an estimate of what the range of possible score differentials we could have seen for that matches. So when we look at the outputs, these guys are all here. And so what we're going to do is we're going to take those things, and we're going to have to do some post-processing to get the visualizations that we want. So first of all, we care about what our estimates of team abilities are. And we think that this is the team ability expressed as their expected number of goals that they're going to be scoring in a match. Because remember, when we have a match outcome, we have the difference in ability between team 1 and team 2, and that's the match outcome. So what these numbers are saying is that the US is probably going to score 1.64 goals, and Spain is probably going to be outscored by a certain amount. And South Korea is really not going to do well, which is surprising because their soccer power index rating put them in the middle of the pack. So the data and the prior don't really line up, and the model is actually overriding the prior and putting South Korea, and I apologize to all the South Koreans. I know they didn't do well. I'm sorry. And now we're going to use the posterior predictive check to look at the replicates of the matches. So this replicate is showing you the central confidence interval for if we redid match number one. If we redid match number one, what do we think the score differential would be? And what we see here is like a super, super wide range of possible outcomes. We are not really very confident about anything, which is kind of appropriate for the situation. But you know, in match number one, it could have gone that the team number two could have won by as much as a goal, or no, probably not actually. It could have been a draw, or team number one could have been up by 2 or 3 goals, or they could have been up by as much as 5 or 6 goals. We really don't know. And so then finally what we're going to do here is we're going to plot the make that chart that I showed you. And, oh, wait, no, first we're going to, yeah, this is just a better visualization of what I showed you up above. So in France versus South Korea, it could have been a draw. In Germany versus China, it was, definitely Germany was going to win. But still, this is a very wide range of information in our posterior. So we're not really very certain of anything, which is exactly what we want to know. This is why we want to be Bayesians, and we want to get this posterior probability distribution, because here we know anything can happen, and isn't that great? So now finally we're going to crunch it all together, and we're going to create this beautiful visualization, and I really need to thank Mitzi and all the PyLadies who put things together for me on this one. What we're seeing here is the red dot is the actual outcome. So if you let your eye drift down this chart, the red dots should actually be on whole numbers. The black dots are just the midpoint of our estimate, and the full line is our 5 to 95% confidence. So as I'm saying, this model is not a great model. There's not a lot of data, but it's a model that's comprehensible. Questions? Okay, well, in that case, we can go to the final part of this talk, and I've actually got enough time for it. What is this talk over? 4:30. Okay, great, perfect. Exactly the right amount of time, because I'm not going into much detail on this last one. This is getting, again, to what Cam was talking about when we want to evaluate our models and evaluate our inferences. So this is sort of like, this is your standard machine learning setup. You've got your model. You want to publish a paper in NeurIPS or JMLR or whatever, and you're going to take your model, and you want a Kaggle competition. You're going to take your model. You divide it up into your training data and your test data. You use training to infer the model parameters. You plug your inferred parameters into your data generating model. You use your and then you get your test data inputs to get your test data outputs, and then you compare your test data outputs to your gold standard, and did you do really well, and isn't that great? This is a case study that's sort of in progress. Bob Carpenter put this together in April, and it's showing you why people say you should be Bayesian. This is basically going through all of the math and all of the mechanics and making it really super clear how evaluation works, what your loss function is, and why in the end, at the end of the day, you really, if you care, if it's very, very important to get exactly the right answer, you really need to invest the time in running a Bayesian regime to get the full posterior probability distribution, which is not always necessary. There are plenty of times when getting a point estimate is okay. In this case study, what he does is he sets up a logistic regression model. So a logistic regression model is your outputs, your observed data is a simple binary indicator, yes, no, heads, tails, 0, 1, live, die, bought, didn't buy. These are the kinds of outcomes that you're making decisions on, and you're trying to figure out what all of the parameters that led up to this outcome are. So it's a logistic regression because it takes things from a binary output and puts them on a continuous scale so that you can actually reason about probabilities. In this logistic regression, there are 50 predictors, and there's a certain amount of correlation between the 50 predictors. So what we do is we simulate data. So we have known values for all the parameters, plug the known values into the parameters, use our random number generator to generate that random sample from the model, and then we're going to test on the model we're going to use different inference regimes to fit the simulated data, and then we're going to check how well does the simulated data match we're going to check how well did our estimates do in terms of evaluating the test data on different metrics of log loss and squared error. And the takeaway message is that we can always get a lower error rate if we've got the full Bayesian posterior. It's a nice case study. It shows you how to set up the evaluations and how to recover the parameters. And I didn't go into more detail because I didn't think that we were going to have time to do it, but I want you to know that this is out there, and this is really your homework assignment. From this talk and from everything I've told you, I hope that you want to go through and work through this yourself. And I want you to know that you could use Command Stand Pi to do this whole exercise. So in Stan, as an inference engine, Stan doesn't just do Bayesian inference. Stan also has optimization routines, so you can do a maximum likelihood estimate. And we have a highly experimental, kids really don't do this, and please, if you hurt yourself, don't blame us, experimental variational Bayes inference. It is what it is. Variational Bayes is trying to take your posterior distribution and find another distribution that's perhaps computationally tractable and easier to compute, and it's going to get as close to what the real unknown posterior distribution is with the simpler approximation. But then you have a simpler approximation. It's a real probability distribution, so you use the mean, but a point estimate of the mean of this estimated distribution to be the mean of your unknown distribution. Maximum a posteriori, which is maximum likelihood, penalized maximum likelihood estimates. This is what you're getting out of just about all of the scikit-learn. It's the standard way of computing the mode, essentially, of your posterior distribution. And if you've got enough data and your model is, or your distribution is well behaved enough, in the limit, the mean and the mode are the same thing, and that's really super great. So maximum likelihood estimation is a fair way to go. What you don't get with a point estimate, however, is the standard deviation. You don't know your uncertainty. And that is why when you do have the full Bayesian posterior distribution and you know both your location, your mean, and the scale of the variance, you're going to be doing a better job at the end of the day. So that is my talk. Questions? Oh, and let's go to thanks. Woo! Thank you. Thank you, PyLadies. Thank you, Women in Machine Learning. Thank you, Team Stan. And here are a whole bunch of references that should answer all your questions about using Stan. Okay, now let's have some questions. Yes?
What's the state of the, I guess, older the PyStan library?
PyStan is just released up to Stan 2.19. And PyStan, by the way, is GPL'd. It is not BSD licensed. But PyStan has a richer set of features in terms of working in Python and getting your data in Python. So CommandStan, if you use PyStan and like PyStan, please continue. PyStan is they're trying to go to something different, but the GPL thing was actually a big deal for a lot of our users. The reason that CommandStan Py is in existence is a really nice guy in the university in Marseille put together the first version of the package, which he called PyCommandStan. And I basically took PyCommandStan, and it's now been completely rewritten, but it was definitely something that needed to be done because everybody was writing their own lightweight wrappers to avoid the GPL problem. Yeah. But the other thing is really that we want to be able to keep up with the Stan releases transparently. So that's a software engineering problem. You really need to make your components as loosely coupled as possible. Otherwise, you've just got a maintenance nightmare. More questions? Yes?
So if I have two models which like perfectly fit, perfectly means all have good R hat and effective value. So how would we compare those two? Would be looking at standard deviation of those two, or how would
Of the R hat?
No. So for example, the example that you showed, there was pooled one, there was unpooled one.
Mm-hmm.
Both have good R hats and effective value.
Mm-hmm.
So in the real world, how would we choose which one is the better?
You have to know your data. You have to know your data, and you have to know your application. Stan is a tool. Yeah. I mean, if you could do the simplest possible model, I think Occam's razor says always go for the simplest. The decisions that would affect that would be how expensive is your data to collect, and whatever's going to be fastest and cheapest is probably the answer. But yeah.
can you check the like standard deviation of the two models and see which one has a narrow standard deviation, so that's more confident?
Yes, and there's a whole set of package. There's this again, these are packages that exist mostly in the R ecosystem for model checking and model comparison. So there's a package called LOO, which is leave one out, LOO, leave one out validation. And yes, the statisticians do have all of these one number descriptions of how well the model fits the data. That's the AIC or the WAIC or the DIC. So you would use the packages, and I think ARVIS has some of this cooked into it to get your actual evaluation of how well the model fits the data. But yeah, there's a whole workflow that this is embedded in. And we're definitely trying to put it all together so that people can just sit down and know that these are the steps that you have to do, check them off the list to know that you're doing good science. Questions? It's been a long day, huh? Okay. Thank you very much.